So yeah, the final few lectures are going to focus on applications of information theory and specifically entropy in extremal combinatorics. Although, like a lot of things in this course, like, I mean, how many times have I said the word convexity, right? Like, it's happened so many times. In some sense, this is again going to be different kinds of applications of convexity and maybe concavity, but it's the same thing, um, but in a different way than we've seen. Uh, so let me take an example. So here's kind of an example to get us warmed up. So imagine I take an infinite sequence, an infinite random sequence of zeros and ones. So for each n, I flip a coin. If it's heads, I put a 1. If it's tails, I put a 0. So in other words, it's a random binary sequence. And let's suppose that I let x be the minimum index, so the minimum I, such that ai is 1. So here's a kind of vague question, but how much information does the value of x reveal about the sequence on average? In the sense of, suppose I learn the outcome of x, so I learn that x is 5. How much does that reveal about my sequence, or how much information do you get from that, from knowing the value of x? And then I want to do that on average, so I want to do that over all the possible values for x. So not a lot of information, yeah. Um, so here though, so in this random sequence, I'm thinking of zeros and ones as being probability a half. So maybe I didn't make that completely clear, but I'm saying, yeah, basically it's a coin flip for everything. Okay, so what I haven't really told you is like, what do I mean by information? So the way I want you to measure information is in terms of bits. So bits are like zeros and ones, right? So 010 contains 3 bits of information, right? 11010 contains 5 bits of information. Yeah, okay. So Abel has put a link in the chat, which yeah, is possibly quite interesting. Right. So anyway, so this is a string of length 3 of 3 binary values is 3 bits of information. So suppose that x is equal to 9. So how many elements of the sequence does this tell us the value of? Yeah, right. So because it tells you got a whole bunch of zeros, right? It tells you that the sequence starts like this: 3, 4, 5, 6, 7, 8, and then 1. Now, what's the probability that x is 9, by the way? Yeah, right. Yeah, so it's 1/2 to the 9, because basically that happens with probability half, 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 9 times. Okay, so from this we can so if we are measuring information in bits, now we can kind of answer this question, this vague question, like on average, how many bits of information does the value of x reveal to us? So, okay, so yeah, basically we did this with one example, but x equals k corresponds to revealing k bits of information, and the probability that x equals k is 1/2 to the k. So on average, the number of bits that get revealed is k times. So you have to take the sum k equals 1 to infinity, k times 1/2 to the k, right? That's how you compute averages, right? So we've done this a few times, but usually we do this with finite things. But yeah, so this with probability 1/2 to the k, you get k bits. So the average is just adding that all up. And okay, if you know how, for example, generating functions work or something like that, you can get that this is 2. So generally x over 1 minus x squared is the sum n times x to the n. If you plug in a half, you get 2. Don't worry too much about that. But so what this says is that on average, the value of x reveals 2 bits of information. So kind of informally, now the definition of entropy is as follows. So if I have a random variable x, then the entropy of x is the average amount of information in bits that is revealed by learning the outcome of x. Now, it's, in that example, we kind of built it up in a way that it was clear what this means. So we're going to have to build up a more general kind of understanding of this. But yeah, so hx, the notation is that hx is the entropy of x. So in the previous example, the entropy was 2, so we would write h of x equals 2. So let's think of a different example. Well, maybe this, let's see how this goes. So suppose I just flip a coin. I let x be 0 if it's 1, or sorry, x equals 0 if it's tails, 1 if it's heads. What's the entropy of x? Actually, it feels like 2, um, but we're measuring in bits. So it actually only reveals 1 bit of information, right? So that's something to keep clear on when as we're doing these things, that we're not measuring the number of outcomes. It's kind of it's not even quite the log of the number of outcomes. It's going to be something more complicated. But when it's something like flipping coins, it's kind of the log of the number of outcomes, or so it's the number of bits. So here it's actually the entropy is 1. Flip 7 coins. What is the entropy of the tuple xi, x1, x2 up to x7? So xi is 0 if the ith coin is tails, 1 if it's heads. 3-ish. No, it's going to be easier. So the question is, if I tell you the outcome of all the xi's, then how many bits have I told you on average? Or it's a bit. When things stop being coin flips, it's going to be a bit trickier than that. But yeah, the answer is just 7. So it takes a bit of getting used to. I would say h of x1, x2 up to x7 is 7. So it is somewhat important here that not only, if you learn the output of these xi's, then you learn 7 bits, but also that all of these 7 or 2 to the 7 outcomes are all equally likely. That is kind of, but we'll get into that in a bit. But is it clear what's going on here now? Oh, okay, fine. Okay, yeah. So basically one coin flip is 1 because, basically learning the value of x is like learning a binary word of length 1, because you just learn a 0 or a 1. So the length of the word you learn is kind of related to the entropy. So here it's 7 because you learn like zeros and ones of length 7, and here it's 1 because you learn just one thing. So it turns out that the way that this entropy thing works is that, like, if you have independent random variables, so think of 2 coin flips, the entropy of the pair of coin flips you get by adding up the entropies of the other coin flips. So the entropy, if you have independent random variables, then entropy adds. So so basically from the first example there, where it was just 1 coin flip and the answer is 1, if you want to know what's the entropy of 7 coin flips, you just add up 1 plus 1 plus 1 7 times. Okay. But so here I'm just talking about a pair of random variables, but this splits up more, right? If I take, 7, then and this kind of makes sense in terms of bits of information. Like if x and y are independent, and if revealing the answer for x tells you kind of on average h of x bits of information, revealing y tells you h of y bits of information, then if I reveal both, then it's told you h of x plus h of y bits of information. Suppose I take x to be a random number from 1 to 16. So this is, and I haven't really told you how to do this, but what would you guess is the entropy of x? So definitely the number of outcomes is 16. I can see that maybe this experiment is not like the best because I haven't told you how to do this, and unsurprisingly, I'm getting a lot of different answers here. Almost every answer has been represented at least once. Ooh, even undefined. That's good. Okay, so the answer should be 4. So kudos to whoever got 4. The numbers 1 to 16 I can think of as being associated to binary sequences of length 4, right? Because there's 16 of them. So, and picking a random number between 1 and 16 is kind of the same thing as picking a binary sequence of length 4, because it's, what I've written down as the numbers is different, but it's not really a different thing. It's just picking 1 out of 16 things at random. Yeah, so the entropy of a random choice of 1 up to 16 is 4, because it kind of tells you 4 bits of information. What's the entropy of the pole? Pretty high. That's a good question, yeah. Yeah, so okay, x is equal to 0 with probability a quarter, 1 with probability a quarter, monkey with probability a quarter, and 10 with probability a quarter. But one thing about it is that the actual outputs of x, like the actual set of kind of values that x can take, doesn't affect the entropy of x. So actually the fact that I put monkey here doesn't matter. So really, x can be equal to one of 4 different things, each with probability a quarter. And really these 4 different things, if I change them to any 4 different things, it shouldn't affect the entropy of x. So you could think of those four things as the numbers or the binary string 00, 01, 10, 11. Totally. Yeah. Yeah. Since they all have the same probability, it is totally reasonable to think of this as like how many bits do we need to represent four unique things? Totally. Or four distinct things, I guess. Yeah. So you can really think of the four different outcomes as being like four binary strings of length 2. And then if you think of it that way, then the amount of information that x reveals is 2 bits. So like h of x is 2. I haven't really given you the tools to like do this yet, but that's the intuition. So the actual outputs of x don't actually matter for the entropy. If I took a random element of a, b, c, d, it has the same entropy as taking a uniformly random element of 0001, 1011, or fish, dog, chair, 7, right? It doesn't really matter. But it matters that all of these things happen with probability a quarter. That does matter. So a way to think about it is how can I generate a random element of the set A, B, C, D? One way of doing it, which, I mean, it's not clear whether this is a natural way of doing it or not, but one way to do it is to define a different random variable y, where y just picks uniformly any real number between 0 and 1. And then we could say, okay, if y is between 0 and a quarter, I output A for x. If y is between a quarter and a half, I output B. If it's between a half and 3/4, I output C. And if it's between 3/4 and 1, I output D. So this is just kind of, for whatever reason, I'm trying to represent x in terms of a different random variable, such that it doesn't change the distribution of x. And this will have the properties we want, right? The probability of x being A will be a quarter, because that's the probability that y lies between 0 and a quarter. Now if we think about information revealed by different outcomes, we can think of it in terms of like how many bits of y, the binary representation of y, get revealed when you learn the value of x, right? So by the way, so binary representation, right? Like if I have the, 1/2 is equal to, in binary it's 0.1, right? And then a quarter is like 0.01, right? Right. So if I learn that x is equal to A, what that tells me is that the first 2 bits of the binary representation of y are 0, 0, right? Because it tells me y is between 0 and a quarter. If x comes out as B, it tells me that I have 0, 0, 1. C tells me 1, 0, and then D tells me 1, 1. Technically, it's possible that y could equal 1, but that has probability 0, so it doesn't really matter. So if you think of it this way, that if I make a random variable y, which generates x, where y is just a random number between 0 and 1, then the outcome of x tells me something about the first few digits, or not digits, but bits in the binary representation of y. And this is a way you can think about the entropy of x. Is that clear? Or is that too weird? Yeah, okay. But yeah, so this is just kind of intuitively what's going on. So the actual outputs of x don't matter. It's really just for each kind of possibility for x, you just care about how likely it is, and that determines the entropy. And you can always think of it in this way, that you generate a random number between 0 and 1, and based on the value of that number, you determine what x is. And sort of the entropy of x will sort of tell me how many bits of the number get revealed by learning the value of x. Sort of. There's a little bit of ambiguity here, because so here we dealt with 4 different values, and that makes it kind of natural to say that it corresponds to 2 bits, because I've got 4 values, 2 to the 2 is 4. What if I had like 7 outcomes, or 5 outcomes, or 6 outcomes? So suppose that x could be any number between 1 and 6 with equal probability. Now, what should my entropy be? Or let's say it's between, n possible outcomes. Each are equally likely, and n is not a power of 2. So anyone have a guess for that? What should h of x be? Yeah, something like that. Except I'm not even going to restrict my attention to integers. I'm gonna allow it to be a non-integer. So just take the log of n. Log base 2. As we're going to find out later, it doesn't actually matter what the base is, it turns out. But since we're doing everything in bits here for now, we can do log base 2. Right. So in some sense, if I have 5 different outcomes, it's sort of like saying that learning the value of x tells me a little bit more than 2 bits of information, but less than 3 bits of information, because log base 2 of 5 is between, is bigger than 2 and less than 3. So it's kind of like it tells me full information about if you think of it like generating x by taking a random number between 0 and 1 and doing, if it's in the first fifth, we give it the first value, the second fifth of the interval, we give it the second value, and so on. You can think of it as saying that if x has 5 different value outcomes and are all equally likely, it tells me the first 2 bits and then kind of partial information about the third bit in some sense. This doesn't completely work, because sometimes it'll tell me like partial information about all the bits or something like that, but in some sense this is sort of the idea. Okay, so now here's a different situation where now we have things that are not equally likely. So let's, I don't think I actually made this one into a poll, so unless I did, no. Okay, but so then let's just talk about it then. So what should the entropy of x be if it's got 3 different outcomes where they're of probability, 1/4, 1/4, and a half? You can kind of, if we again think of, maybe don't divide things by 3, but something like, actually the 4, I also don't like the number 4 here, because if all the things were equally likely, it would be, you'd be revealing 2 bits or whatever, if there's 4 different outcomes. So imagine I break my interval 0 up to 1 into half, and then I break the first half into half. And you could generate a random variable y, where if y is in here, it corresponds to, x equals a, and this corresponds to x equals b, and if y is in here, then I have x equals c. If y is in the first quarter of the interval, that tells me that that's the same as saying that the first 2 digits or first 2 bits of y are 0, 0. So y equals 0, 0, and then something is the same as saying y is in 0 up to 1/4, right? If y is in here, it tells me that it starts with 0, 1. If y is in here, it tells me it starts with 0.1 and then anything, right? So it's kind of like, so I want, the entropy is the average number of bits that you learn. So with probability 1/4, I learn 2 bits, and then another probability 1/4, I learn another 2 bits, plus a half, and with probability half, I only learn 1 bit. So, okay, so then it's like a half plus a half plus a half, so 3 halves. Okay. Yeah, I'm not sure if this kind of, maybe I should have just given you the definition rather than building it up this way, but this is kind of how it works, kind of on an intuitive level. So, right, so the answer is 3 halves. So finally, let me just kind of, stop building it up like this and just give you a definition. So the entropy of so suppose x is a discrete random variable. Discrete random variable just means that, like, so it could have infinitely many outcomes or maybe countably many outcomes, but it has the problem or the property such that if I look at all the things which have a non-zero probability and I add up the probabilities, it equals 1, which is not the case when you deal with something like a continuous random variable where you have to take an integral. So here we're not doing integrals. It's just a discrete random variable, so everything is just taking sums. So the range of x is all the values which have non-zero probability. So this is just a definition. Range x is all the little x such that the probability x equals little x is non-zero. And when I say that it's discrete, what I mean is that if you sum up over all the things in the range, you compute the probability and add it up, it equals 1. So the entropy of x is, so it's the sum over all little x in the range of x. So sorry if my little x's and big x's look the same, but this is a little one here, of the probability x equals x times the log of 1 over the probability that x equals x. So what you should think about is, the way you should think about this is that, and maybe I make this base 2, but it doesn't actually matter, but we can make it base 2. So if you think about just this part, the log, so you think about that as being kind of the number of bits you learn when you find out that x equals little x. So if the probability, for example, that x equals little x is a quarter, then kind of revealing that x equals little x kind of reveals 2 bits of information. If it was an eighth, it reveals 3 bits of information. If it's, the probability is 1 over 100, it reveals log of 100 bits of information. And now the sum is just computing the average, right? So remember, h of x is supposed to be the average amount of information. So you should go over all the different outcomes, compute the amount of information revealed by learning that outcome, and take the average, which is just summing over, summing the probability of that over all the outcomes. Is this clear? It's still probably quite weird, but so one thing about this is that, like I said with this monkey example, that this doesn't actually depend on the actual values in the range. It just depends on how likely each thing is in the range. Yeah, this is just the expected number of bits learned, totally. Yeah. So if you think of this thing I've underlined in green as being number of bits, then this is just computing the expectation or the average or whatever you like to say. Probably, I would say discovered. This is not made up. There is something magical about entropy that's like, it's natural, but it doesn't feel natural when you see it for the first time. But I think this was made up or discovered, I should say, by Claude Shannon, I think. So you might, there's I actually once took a course in information theory, and like entropy is a big thing in that, So we're going to basically be using this entropy, which is part of this information theory thing, to prove things about combinatorics. Okay. Now, so I wish I was done with definitions, but we actually need another concept, which is conditional entropy, so the way to think about conditional entropy, so if suppose I have random variables x and y, 2 different random variables. Conditional entropy is kind of, I think if we were in a continuous world, you'd want all the sums would be replaced by integrals, but it would just be a single integral. I mean, unless you're dealing in a 2-dimensional space and then it's a double integral. But okay, so now kind of conceptually, what is the conditional entropy? So kind of so the way to pronounce this is like entropy of x given y. So the line is kind of given, is the average amount of additional information that you gain from learning the outcome of x after you've already learned the outcome of y, which is not just the same as the entropy of x, right? Because it could be the case that, like, suppose I take a number between 1 and 100, right, as y, and then I reduce that number mod 2, and that's x. Like x is 0 or 1 based on whether y is odd or even. Then if I know the value of y, then how much additional information do I get by learning the value of x? And you don't get any, because if I know y, I can compute x, right? So so it's kind of it's the additional information you get from x after you already know y. So the definition of this is as follows. So first I want to define the entropy of x given that big X is equal to little x, which is kind of technically it's kind of the same as the original definition of entropy, except all the probabilities you compute are like subject to x equals x. And then to compute the conditional entropy of y given x, you sum up over all the x's in the range of y, of x. You compute the probability x equals x, and then multiply that by this the entropy of y given that x equals x, which is just the average of, or the expectation of this thing, kind of overall choices of little x. But the way to think of this is it's the average amount of information you get from learning the value of y after you already know the value of x. So that is a good question. I mean, I get mixed up with these things as well. So the first one is kind of so like, this thing versus this thing. So this one is kind of looking at a particular outcome of x. and saying, how much does that particular outcome of X tell me about Y? Or in other words, or it's kind of the opposite of that. It's kind of like, if I know that X equals this particular value, how much more information does Y reveal given that? So for example, if I say, suppose every time, so I have two random variables X and Y, and whenever X is equal to 0, suppose I know that I automatically know that Y is equal to 0 for some reason. Then in some sense, knowing X equals 0, if I know that X equals 0, then Y reveals no additional information in that case. Whereas this one is kind of averaging that out over all possible outcomes of X. So, okay. Yeah, so it's kind of like, knowing that X equals a different value might have a different influence on Y. And this is kind of averaging all of those different things out over all the possible choices for X, which, yeah, it's difficult to wrap your mind around these things. But yeah, I don't think I can like impart the information, the intuition on you through this. But I think if you play around with it, and as we kind of do some more examples and stuff, it might become more clear. Okay, so actually this is kind of the example I was kind of mentioning. So suppose I let Y be a random number between 1 and 100, and then I let X be just Y mod 2, meaning X is 0 if Y is even, X is 1 if Y is odd. So I'm trying to get you to do this without doing the calculation, actually. I'm not sure if that's going to be possible. But one of these things is easy. So what is conditional entropy of H given, so Y given X? So this one I think is a little bit more complicated. I would start with the second one. What's X given Y? So if I know the value of X, how much additional information do I get by learning the value of, if I know the value of Y, how much do I learn if I then reveal the value of X? And then this one, so kind of in the other direction, if I know the value of X, that's like saying that I reveal to you, okay, whether X is or Y is odd or even, then how much additional information is there to be gained by learning Y? That might just, for which one? Yeah, so for H of X given Y, the way you should think of it is that, so let's say we're trying to figure out what is X and what is Y or something. And I tell you the value of Y. I tell you Y is equal to 62. And then somebody else tells you that X is equal to 0. How much information did you really get from the second person, I guess is the question. Yeah, it's going to be 0 because from knowing Y, you could already compute X. There was nothing left to know about X. So yeah, this second one is going to be 0. The first one is like, okay, I come along and I tell you X is 0. And then someone comes along and tells you Y is equal to 42. So how much additional information did you really get from learning Y after I told you that? And it's kind of like you had 50 choices. They were all equally likely. So that should be log base 2 of 50. So yeah, it takes a little bit of thinking, but if you kind of think through these examples, I think yeah. And also always remembering that it's the number of bits, not the number of outcomes we're looking for. So this is a kind of full slide. Yeah, okay, I want to prove things using entropy. We need to know some properties about entropy. And in some sense, like, we're not going to need to look so much back at the original definition of entropy. All we're going to need to know is these properties in order to prove stuff. So all of these things can be proven by just looking at the basic definitions, but yeah, we probably won't need to go back to the definitions again. So suppose I've got a bunch of random variables, x, y, z, x1 up to xn. They're all just, let's just assume that they all have finite ranges because everything this is combinatorics. Everything's finite. Okay, so here's some facts. So remember we said if I have n possible outcomes and they're all equally likely, then the entropy should be log n. And the first kind of fact here says that if you had n outcomes and they're not equally likely, or not necessarily equally likely, the largest the entropy could possibly be is log n if you have n outcomes. So, and it's equal to log n if and only if all the outcomes have the same probability. So S, remember, is the range of X. So the entropy of x is at most the log of the range, the size of the range. Possibly the most complicated one of these is the second property, but it's also intuitive. So I really recommend remembering the intuition, which will give you the result. But so this says that the entropy of the, if you think of the tuple like an n tuple, so that's just a random variable. So if I have n random variables, then if I just take the n tuple x1 up to xn, that's a random variable. The entropy of that random variable is the same thing as the entropy of x1 plus x2 given x1 plus x3 given x1 and 2, and then x4 given 1, 2, and 3, and so on up to xn given x1 up to xn minus 1. And intuitively, we kind of saw that on the last, in some sense, we saw that on the last slide in the poll. It's kind of like, okay, maybe not exactly, but the idea here is that how much information is kind of revealed by learning x1 up to xn. It's the same as saying, okay, how much did I learn from finding out the value of x1? And then how much more did I learn by finding the value of x2? And then given that I already knew x1, then how much did I get from learning x3 given that I knew x1 and 2? And then 4 given 1, 2, 3. So it's like you have this base amount of information from x1. This is how much additional you get from 2, then how much additional you get from 3, and so on up to n. So suppose I do these indices in a different order. Like say I write down h of x2, for example, and then I write h of x1 given x2, and then maybe I go with 3, h of x3 given x1, x2. So this is it's gonna compute the same thing. Yeah. So the individual values are different. This is different from that. The total value when you add up everything is the same. The individual terms might be different. So this might be different from that, but it turns out the sum of these two things is equal to the sum of those two things because it'll just be h of x1, x2. So I can break up h of x1, x2 either way. x1 plus x2 given x1 or x2 plus x1 given x2. So, and this you can derive just from it's a bit of algebra, but you can derive that from the definition of conditional entropy, that these things are the same. It's probably just a case of like switching a sum or something, or yeah. And by the way, this is kind of like how probability works, except that sums have been, yeah, totally. And so this is a monkey and then this is 10. And if you do it in the other order, you get the same amount of like total information. But you can get if you think of this example from before where I pick a number between 1 and 100 and then I reduce it mod 2, if I reveal just the number between 1 and 100, it gives me log 100 bits of information. And then the second one gives me nothing. And yeah, exactly. But the other way around, if I reveal the number reduced mod 2, that gives me 1 bit of information. And then log of 2, log 2 bits of information. Then I reveal the other one, it gives me log of 50. Log of 2 plus log of 50 is log of 100. But anyway, this is kind of like I don't know if you call this Bayes formula or whatever for probability, except that the product has become a sum because of taking logs essentially. So it's like, probability of E and F is probability of E times probability of F given E. If I have two events, E and F, right? And this is kind of the same thing, except things are summed because when you take logs, products become sums. It's kind of related to that. Okay, so this is kind of, if you think about the information, this is kind of a simple thing to reason, but to prove it, you need to know something about convexity and that sort of thing. But or maybe, yeah, I think that's what you need. But so if I already know y, then telling me x after I know y reveals at most as much information as it would have if I just didn't know y and I just learned x. So yeah, so already knowing some information can only decrease the amount of information I learn. So if you had already taken a course in extremal combinatorics before you got here, the amount of information you would have learned from this course is less, right? Possibly. Okay. And if something is already completely determined in terms of another random variable, then yeah, basically learning. So if z is determined by y, kind of like my reducing mod 2 or whatever thing, then the entropy of the tuple yz is the same as the entropy of y, which is the same thing as saying the entropy of z given y is just 0. Okay, so so next time hopefully we'll be able to use this to prove some stuff. Oh yeah, so this is just kind of a kind of reason for some of these things. So this thing about the log of the range, turns out it's just an application of Jensen's inequality, which I maybe won't go through, but it's using the fact that x times log of 1 over x is concave, and this is like what shows up in the like, you know, in the kind of formula for entropy. It kind of has like this function in it. The fact that that's concave implies this upper bound. Like I said, B just follows from the definitions by kind of playing around with algebra. Okay, and all of these things are just kind of from the definitions. Okay, so how are we going to actually apply this in combinatorics? So the way we're going to kind of apply this is as follows. So let G be a graph. And suppose I want to prove an upper bound or a lower bound on the number of substructures of G of a certain type. So the first thing what we're going to do next time is prove, like, suppose I have a graph and I want to upper bound the number of perfect matchings, for example. And this graph has some kind of special properties. Okay, one way you can upper bound the number of substructures is to say, okay, or upper or lower bound, is to say, okay, so I'm going to take a random substructure of that type. So for example, I could say, take a random perfect matching in this graph. Now, okay, so if I've taken a random perfect matching or whatever, the entropy of that random perfect matching is at most the log of the number of perfect matchings, because that's the range of this random variable. So that's by property A from before. And if I chose my perfect matching uniformly at random, or whatever kind of substructure, so it's going to change later, but the first thing we'll prove is about perfect matching. So if I pick one uniformly at random by just saying, okay, I take all the perfect matchings, I pick one out of a hat, then you're going to have equality here, that h of x equals the log of the number of perfect matchings. So in that sense, it becomes kind of clear that actually bounding the number of perfect matchings in your graph is the exact same thing as bounding the entropy of a uniformly random perfect matching. Because if it's uniformly random, I have equality between h of x and the log of the number of matchings, perfect matchings, whatever. If I wanted to prove a lower bound on the number of perfect matchings or whatever substructure, then even if I don't choose x uniformly, I could choose it non-uniformly in some way, but it suffices to prove a lower bound on h of x, and then I'll have a lower bound on the number of substructures. So essentially, bounding this entropy can translate into a bound on the number of copies of a certain substructure in a graph. And that's the way we're going to use it. So first, we're going to kind of use this for an upper bound problem. But for that, we have to choose a uniformly random structure, because we need equality here. Because if I prove the entropy is at most something, I need this to be equal in order to get an upper bound on the number of substructures. And the second thing we're going to use with entropy is proving a lower bound on the entropy in another problem, which is going to be homomorphism densities of trees. And that'll translate immediately to a lower bound on the number of homomorphisms. That's a good question. How could you find the distribution? That by just saying it in words, I guess. For example, if I say, I've got a graph, and okay, suppose we know it has some perfect matchings. You could just say, pick one at random. Like put them all in a bag and pick one at random. And you don't really need to know how many there are to say that. And yeah, for counting, say, homomorphism density of trees, it's going to be a more complicated distribution, but yeah, also something you just say in words. Yeah, so to compute h, so we're not going to compute it exactly. So it's going to be like, pick one at random, uniformly at random. I know that this equals the log of the number of perfect matchings. And now I want to upper bound the entropy, but not actually compute it. So if you're upper bounding it, you can throw things away, and that's kind of going to be the idea.